All right, guys, Mr. Antonucci here, and in this second video, we want to talk about how to calculate a confidence interval for a difference of two proportions. So when the conditions are met, we can use our familiar formula to calculate a confidence interval. And remember, the general formula is your point estimate plus or minus your Z star critical value times the standard error or the margin of error, depending on which situation we're working in. So for here, when we have two population proportions, we have a C% confidence interval for the difference in population proportions is, so the point estimate is going to be the difference in sample proportions plus or minus the Z star critical value, dependent upon what confidence level you are looking at, and then times the standard error of the statistic. Okay, so here we go. On the AP formula sheet, you're not given this specific formula, but what you are given is the general formula of the statistic plus or minus critical value times standard error. This line is literally in the formula sheet. And then elsewhere, they will give you the standard error for the difference in sample proportions. And you have to know how to use this general formula, statistic plus or minus critical value times standard error of statistic, how to use that general formula in this specific situation with the other formulas. Okay, so let's run into an example here. We're back to that Gallup poll previous, and we want to calculate a 95% confidence interval for the difference in proportions. So the first thing we're going to do is our point estimate, which is 0.39 minus 0.66 plus or minus. Now we have to figure out the Z star critical value. So since we're doing a 95% confidence interval, we can use a table of values. But remember, 95% is right here. That's the middle 95%. That leaves 2.5% above and 2.5% below, because the middle 95 misses the outer 5%, which is split among the upper and lower half. Since I'm looking at the positive z-scores, I need to find the z-score for this point right here, which is going to give me the probability of anything less than that z-score, which is 97.5%, because it's from that z-score all the way down. Okay, which translates into 0.975. So I find 0.975 on the table right here, and this corresponds to 1.96. So 1.96 times the square root of 0.39 times 1 minus 0.39 over 811 plus 0.66 times 1 minus 0.66 all over 800. Okay. Now, if you perform the calculations, you're going to negative 0.27 plus or minus 0.047, which is going to give us a confidence interval of negative 0.317 to negative 0.223. Now, I didn't write it incorrectly because remember, these are negative numbers, which indicate, so the lower number would come first, which is more negative than negative 0.223. So the way we would interpret this confidence interval is we would say we are 95% confident that the interval from negative 0.317 to negative 0.223 captures the true difference 2021 to 2020, or 2021 minus 2001, in the proportion of all U.S. adults who saw a movie in a movie theater during the previous year. Now, a couple things to remember is we don't want to say percent when we mean percentage points. Okay, so the decrease between 22.3 and 31.7 percentage points, that's not the same as a decrease of 22.3 to 31.7%. So there's a difference between percentage points, which is just how much the raw percentage went down, versus a percentage increase or decrease, which is a percent of some other whole, um, giving it increase or decrease. So I want to talk about how to construct the confidence interval if we're going to use a calculator. So what you want to do is open up your TI-83 or TI-84, whatever you're using. I happen to have a TI-83 Plus here, so I'm going to clear all this off. And then the first thing we want to do is um, go to Stat, then over to Test, and then we're going to scroll down to 2 proportion Z interval, not 2 proportion Z test, 2 proportion Z interval right here, which is actually choice B. Okay. And then what we're going to plug in is our data the way that we plugged it in up here. Okay. So if we look at that, I did X1 was 2021 information. So that was 316. That's the number of successes. The sample size is 811. And then the number of successes for the other one is 528. And then the sample size for that one is 800. Notice that the C level, we have to put the confidence level in as a decimal, so that's 95%. If I hit calculate, what this is going to do is give me p hat for the first and second samples, as well as the confidence interval here and the sample sizes. Note that it did the samples um, in the order 2021 minus 20 or 2000. So if you wanted to do it the other way, you would just have to put the information in backwards. So instead of 316, 811 here, I'd put 528 and 800, and then 316, 811 here. Okie doke. So with that, on the formula for the difference of population proportion often is going to lead us to errors by students. So it's helpful if you do it, and I recommend you doing it on the calculator. But when you get to performing the full uh, constructing the 4-step process for constructing a confidence interval, you want to make sure that you're still doing the state, plan, and conclude steps in addition to the do step, which basically the do step is figuring out the confidence interval, which you can use the calculator for that. So before we wrap up this video, I just want to make a note about doing inference for experiments. So if we look at this example here to motivate us, we have an experiment to compare treatments for prostate cancer. 731 men with localized prostate cancer were randomly assigned either to have surgery or be observed only. After 20 years, p hat sub s is 141 over 346 or 0.387. Of the men assigned to surgery were still alive. And p hat sub o equals 122 over 367, which is 0.332 of men assigned to observation were still alive. The parameters in this setting, so we've defined the parameters in this situation. So the important thing is that there was no random selection here because most experiments rely on volunteers as subjects. You run into ethical problems if you're randomly sampling people and requiring that they do a some sort of experiment. So, in that same logic, often will apply to experiments on animals or things. So, the way the random condition is satisfied is in the uh, random assignment of the individuals. Notice it's randomly assigned here. So, just a little note about inference, and we looked at this a couple chapters ago. You can have random selection and then also random assignment. Optimally, you want to do both because you can make inferences about the population and inferences about cause and effect. Because if you are randomly assigning groups, then you can make inference about cause and effect. If you're randomly selecting them, you can make inferences about the population from which they were selected. So if you can do both, that's wonderful, but you can't always do both. You often can only do one or the other in a situation. So just want to keep that in mind. If you are doing an experiment and you can't randomly select the individuals, you can only randomly assign them to groups, well, then the 10% condition isn't going to apply when you're doing a confidence interval. So just a note here, many students are going to lose credit when defining parameters in an experiment because they describe the sample proportion rather than the true proportion. So for example, the true proportion of the men in the experiment who had surgery and survived 20 years describes P hat sub S, not P. So notice how they said the true proportion of men like the ones in the experiment, like the ones, not of the men in the experiment. Okay? All right, guys, that wraps it up for this video. Got one more for this section. We'll do that next.